The first speaker that we have today is by Ben. Do you want me to give you a little introduction?
Sure, yeah.
Sure. So Ben Bogart is a Vancouver-based interdisciplinary artist working with generative computational processes involving physical modeling, chaos feedback systems, and computer vision and machine learning. And he's been inspired by knowledge in the natural sciences, including quantum physics and cognitive neuroscience. I guess that's an interesting place to maybe leave it there for your bio. And today he's going to talk about machine subjectivity.
Thank you, Nora. I forgot I had to pick up the second microphone. Hello, everybody. So I am going to be talking about the subjective machines, and part of this is supposed to be a little weird and challenging, so feel free to push back on everything. So I'm interested in subjective machines because of my work with machine learning, and I'm going to call them learning machines because I'm interested in thinking about them as objects and methods, not necessarily disciplines. Machine learning is a discipline. And so learning machines are something that I've been working on since about 2007. So they've been quite integrated in my practice. And I've been thinking about them in a particular way through exploring them in various artistic manifestations. So I think it might be worthwhile to talk a little bit about how I think about these machines that learn. And part of that is because there's just so much hype and mystification about what they can and can't do. And so I would define learning machines as any system that can improve their performance on some task autonomously. Often the conduction, the performance of the task involves some kind of statistical model. Sometimes the machine learning's purpose is only to make a statistical model. But at least in the kinds of things like deep networks we're talking about most often these days, and the leaps and bounds these technical systems are reaching, those are almost always exclusively being conducted by a statistically oriented machine learning system. So I want to really enunciate and emphasize that the kinds of models constructed by learning machines are the same kinds of models that human statisticians would make. There's nothing miraculous about learning machines. They are not magic. They are not necessarily the future, but they could be. So why are they special if they're just more statistical models of which we have no shortage? I think of kind of two poles. One is a pro and the other one's a con. The pro and the real reason why they're so popular and we're talking about them so much is the degree to which they're scalable. We can make really, really big statistical models trained on lots and lots and lots of data now. And we can do it in a way that's much more cost effective than it would have been had we done it with human statisticians, even those using computers. So the big part of why things are so popular is that it's cost effective. It has a value in a capitalist system to autonomize even statistics. But the con is to what degree they are actually interrogable. And by that I mean, how much can we question their results? How can we have a conversation with them about why they have made a statistical conclusion? And they're not very good at that, especially the deep networks we're talking about most often when we talk about machine learning today. So they're really black boxes that are opaque and invisible. And as they're deployed in all kinds of contexts through social media and marketing systems, in a capitalist context, we have to be really careful about what they could be saying about us in terms of the models they're building. And so for me, one really big question is, how do we validate these models if the only cost-effective way to produce them is by building another giant machine learning system that does the same thing? If we can only compare them to each other, because we can't compare them to a model constructed by a human, how do we know they got it right, especially when we can't interrogate it? So that's my entry point for subjective machines. It's kind of pushing against this idea of the objectivity of the statistical model in the context of autonomous machine learning systems. So I'm not going to define, well, I am going to define subjectivity, but I'm going to define it in a very narrow way that comes out of my practice in thinking about learning machines. So a subjective machine, the idea of subjective machines is a framework for thinking about objectivity and subjectivity, both in autonomous machines and also in brains that are in biological material. And this kind of follows from my PhD work, which was funded by the Social Science and Research Council of Canada on making a machine dream. And you can ask me more about that later. I'm not going to talk about it. So I'm going to get the definition out of the way right away and then talk more about details. But I define subjectivity as an interaction between sensation and imagination that forms a reinforcing pattern resulting in perception. Simple enough. There are two philosophical assumptions behind this definition of subjectivity. There's probably more, but these are two that I'm picking out. And these ones are really important to me because they're my own personal beliefs also. The first is that the world independent of cognition, that is the world that we cannot conceive of, that is beyond senses and perception, is actually there, but it is unevenly distributed and continuous. It's not made up of discrete chunks of things, although some physicists would disagree. And second is, following from Merleau-Ponty, this idea that you can't have a concept of what a subject is without already having a concept of what an object is. That the idea of point of view and experience infers a relationship between two different sides, a thing to be perceived, but also a perceiver who is able to extract that thing from its world and think about it as something independent. So if subjectivity is this interaction between sensation and imagination, what do I actually mean by imagination? I think imagination is the ability to construct things that aren't a mirror of the outside world. So one way of thinking about that could be novelty generation. But I would define it as a cognitive process that facilitates the generation of internal subjective representations, in particular including mental images. So what is sensation? Sensation allows information from the world as independent of cognition, that thing outside of us, to implement those same subjective representations. So what's the relationship between sensation, imagination, and a machine? So those definitions of subjectivity definitely apply, at least in my thinking, to biological agents. But maybe the idea of machine imagination is a little less clear. And so I would define machine sensation, for example, as the representational information patterns that are fed to a computer, and they're often called the training data or a corpus of information, a body of information. And those are most often measurements of something. It could be atmospheric measurements or an image from a live camera or almost anything. The flip side of that is imagination. And I think of the imagination of a machine as being implemented by unsupervised machine learning algorithms. So I'm not going to get into what that means very specifically beyond saying an unsupervised machine learning algorithm is like a classifier. It decides that in this space of measurements, which things belong to cats, which things belong to dogs, which things are associated with maleness, which things are associated with femaleness. And I think of that classification problem as the projection of boundaries into that underlying continuity that is independent of cognition. So here we have a whole bunch of points. This is about 10,000 individuals. The x-axis, I believe, is height. The y-axis is weight, but I could have gotten those flipped. Doesn't really matter for the purposes of what we're going to talk about. And this is classified or labeled data. So the white dots mean one thing, and the black dots mean something else. So we might guess that since we're talking about body mass, that there could be a gender thing going on here. We can see that the images at the very top here, there it is. Above a certain point, there are mostly white lines. Below a certain point, there's mostly black points. And then the same thing for the extremes on the other axis. And so sure enough, if we plot the means, which are very hard to see, but that is the mean of the black dots, and that's the mean of the white dots, we can say that yes, on average, men tend to be taller and heavier than women who tend to be smaller. I'm bringing this up because, as we can see, this data is very, very messy. And this idea that there are two categories, men and women, as separable by some property, as in body mass, means that there's a lot of things that are lost. There are a lot of women that are really, really exceptional. And then there are a few men that are extremely exceptional. And so what's important to me here is this thinking about that underlying continuity, that when we're measuring the world, less biased, measurement always includes some bias, but less biased by cognition, that there's a lot going on. The classification problem, the deciding which are men and which are women, involves projecting these imaginary boundaries. And my argument is that those boundaries are fully imaginary because they can have multiple positions. We could draw a straight line that bisects the two means, or we could invent something really bizarre. And I would say a lot of the kinds of knowledge conceptual representations that are generated by machine learning algorithms these days probably look a lot more like this than they do a straight line. So the question of arbitrariness and kind of generative processes and imagination is always implicit at the very bottom level of these systems. So I say these are imaginary because there's no single objective solution for dividing those two spaces, that they're conflated. They are continuous in their essence in an underlying fashion. Different similarity methods and different algorithms would draw different kinds of lines, and that really changes how people fit into those categories. These boundaries that define groups allow us to group sensory information into different camps. So we can think of a kind of proto-concept, or in the case of my work, I call them percepts, very low-level abstractions of sensory information that refer to a category, for example, male or female. And so the contents of subjectivity emerge from this interaction between the underlying data itself, that there is a distribution, there are measurements that can be made of something independent of us, but there's always necessarily this act of projecting imaginary boundaries onto that continuity. And so I would say subjectivity is this emergent interaction between those two forces, between what the world as independent of us imposes upon us and what our processes of imagination impose upon that external world independent of us. So to summarize, the basis of subjectivity, and also I would say also the basis of all of cognition, is perceiving two different sensory patterns as belonging to the same imaginary class. It's seeing two leaves and just thinking they're a leaf and not attending to the uniqueness and individually measurable properties of each. Every moment in time is a unique moment. We can only make sense of anything by grouping things by similarity. So what is the point of this? I think it's a useful way of breaking down the kind of magic around a machine learning system just being a big black box of objective knowledge, because it allows us to poke it in certain ways to see what are the different components that are actually informing the kinds of knowledge or the kinds of models that they're actually producing. And not only that, we can also use this kind of framework for thinking about both our machines and ourselves in a way of interrogating our own bias and prejudice around the imaginary concepts that really constitute our lived experience. So we can ask very specific questions of the black box. How sensation is represented? How are we measuring these points? What is preserved and what is removed? How do those people who are on the wrong side of the line fit into the model or not? What are the similarity measures being used? How are we comparing apples and oranges? And whether those ways of comparing things are actually valid culturally or not. And of course, finally, the summation of all those things is where the boundaries between classes in this continuous space that is beyond our comprehension, where they actually end up. How much time do I have? Perfect. I can go through this really slow and easy then. So watching and dreaming is my current body of work, and I'm taking the kinds of learning machines that I had been using in previous work, except I'm applying them to the appropriation of popular cinematic depictions of artificial intelligence. And right now I'm working with Blade Runner, 1982, the original, 2001: A Space Odyssey, and Tron, which are all 80s movies that kind of cue some kind of science fiction future, but are also a time where artificial intelligence kind of started growing in it was one of these early humps of growth of machine intelligence. So in this appropriation system, the original film itself, both the frames and the sounds, are the machine sensation. So the world perceived by the machine is the world of a film. So the title of the work is Watching and Dreaming. The dreaming more refers to my PhD work, and I'm not going to talk about that too much. And this is kind of a false dichotomy between watching and dreaming, because the argument of my entire PhD is that watching and dreaming are continuous. It's one system of simulating mental images. So watching is more an emphasis on how sensory information allows the construction of mental images through these subjective processes. And that is how we make sense of the world. That is our own kind of perceptual system, but it's also how the machine makes sense of 2001: Space Odyssey, for example. Dreaming is a little more complicated, but we can think about it as relating to time. So dreaming is more about the occurrence of events over time rather than the kind of construction of a individual moment in time based on sensory information. But again, that's a false dichotomy. So watching 2001: A Space Odyssey was very recently completed. Its first exhibition will be as part of a triptych of works showing versions for Tron and Blade Runner at the Surrey Art Gallery in April. And so I'm just going to step through a concrete visual example of this process of subjectivity. So this is an original frame from 2001: A Space Odyssey, where we see Hal, who's highlighted by the light in the panel. He's a disembodied robot with a camera that can see around. And he's playing chess, which is a nice proxy for how we used to think about machine intelligence. Playing games must be the ultimate of machine intelligence because it's hard for us. Seeing, being embodied, using objects, that must be easy because they're easy for us. But it's totally flipped in the other direction. And he's playing chess with somebody he kills in the film. Sorry, spoilers. So what does it mean to project boundaries in this continuous space? So we know that that original frame is unevenly continuous, meaning some parts have more color, other parts don't. There's different kinds of densities. There's all kinds of things happening. But to make the machine make sense of it, we have to break it into pieces. And that is this imposition, this imaginary projection of lines and boundaries in that continuous space. So this is a depiction where each colored region is one piece that is bounded by these imaginary projections. Once you do that, you can extract each of the pieces are within those boundaries, and these are all of the components from that first frame. And you do this, or I do this, for every single frame in the entire movie, which results in 47 million little image pieces. So one thing about the fact that there's 47 million image pieces is that's just a massive amount of data. So in my case, there's actually two layers of subjective imaginary construction. First, there's this projection of boundaries into the continuity to construct these things. Then the second level is to project boundaries in the space of all of these things in order to reduce what is perceived as redundancy. So we can see some of these are all very similar to each other. So you could imagine to reduce the amount of information, we could just group all those together, and by grouping them, we're constructing these percepts, which are again a function of making boundaries between things that are similar and things that are different. And so once you group all those together, I used an algorithm that averages all of the ones associated with each percept. So all of those purple squares get averaged to one kind of image. All the red things will get averaged to something else. And one component of this project is to make large-scale collages that are intended to be 48 by 48 inch light boxes. So we can't quite get a good sense of, oh no, this is horribly low resolution. They are about 15,000 pixels wide and the same size as they were in the original film. So this is these percepts. They're the higher level abstractions of that sensory information, but they are the 5,000 largest And that 5,000 largest tend to be the ones that are the most unusual. They're the furthest away from the others. And that's why they have such hard edges. So these really bright colors in these corners and the really large framed sizes, like over here, are all because those are ones that weren't easily grouped into categories. So those are those exceptional men and women that don't fit very closely in their own classes. They're kind of out on the edges of things. And so if I use this vocabulary, that's the visual vocabulary of the system, watching is this process of constructing this mental image that is how the machine, we can imagine the machine sees that first frame, where each of the pieces extracted from the original are actually represented by their nearest percept, that is the higher level abstract representation that is most similar in terms of its features to that lower level piece. And you end up with something that resembles the first frame, but is also dissimilar from it. And it's somewhere between, and each of these can approach like a Gaussian distribution where the edges become really soft because there might be a lot of individual components associated with each of them. So I'm going to finish with just a little statement. And by talking about machine subjectivity, my hope really is that we can all consider the degree to which both our machines and our own mental processes are biased and not representations of reality, but really imaginary, creative constructions in our minds. They just happen to be synchronized by the fact that we live in the same world. So we have that same underlying sensory information. And so maybe we should be considering the validity of all concepts in terms of this idea of a subjective point of view. A subjective point of view being a particular combination of similarity measures, that is, deciding things are similar or different, abstract representations of things constructed from those similarities and differences, the contents of boundaries that are projected imaginarily, and also that underlying information distribution, that thing that is independent of cognition, the actual numbers that informs that whole system. And I think by thinking about all these things in the context of machines and ourselves, maybe we can get better at understanding diversity and the idea of where mean fits in with validity of statistical models and also just computational ways of knowing the world.